All right, so now for the full-fledged implementation of this forward Fulkerson process. So what you can see over on the left is going to be a copy and paste of a bunch of those things that we just got done chatting about. The only new things that I've added is I have to start with an initial flow. So if you remember how forward Fulkerson works, is that you're going to take your initial network and you're going to zero everything out initially. Is that those all become my capacities of which I have no flow. So it's going to be 0 of 0, 0 of 16, 0 of 13, 0 and 0 and 0. So what I'm going to do there is create just that initial flow. So it's going to eat the network, and then it's just going to make 0 comma whatever network value is, and then return that thing back to the user. So that's my first function that I technically needed. I didn't need it before because I was starting in the middle, but now I technically have it. I have my augmented flow, my construct residual network, my tree construction, path construction. And then the last thing I'm going to have then is my actual forward Fulkerson algorithm, kind of the calls of all of these. So it's going to eat the network. It's got to initialize it, construct a residual network, build a tree. As long as the tree is actually not kicking out false, so I have a way to go from source to sink, keep on doing some things. Once I'm doing things, I'm going to build my path. I'm going to augment my flow, construct a new residual network, find a new tree. If the tree has an actual path, i.e. there's a way from S to T, keep on going. The moment that doesn't work, so this breadth first tree, if it ever returns false, it's going to kick me out of the while loop, and then I'm going to enter my returned portion of things. So over on the right, then you're going to see a variety of printouts. The first of which is going to be our Canadian goods transportation side of things. So I have this maximal flow, which was achieved after 3 augmentations. Let's actually go ahead and print off the paths. It's kind of nice to see what it would have done. Let's give this another run. Yep, let's clear it out and then give it another run. All right, so what's going to happen here is I have my example 1. Officially, the first 3 printouts are then going to be the paths that were generated. So it first went across the top, then it went across the bottom, and then it did the zigzaggy through the middle. So it went up by 12, then 4, then 7, for an overall flow value of 23. So cool. Example 2 is actually the example that you have in your activity. So we have slightly more involved. So we have 7 total nodes. So a source, a sink, and 5 middle things. Before we only had, 4 middle things. So we increased the ante. Wait, sorry, 0 and 7, there were 6 middle things, if I can count. So 0 up to 7 means 8 things. So you had 6 middle ones. So in that scenario, if you go back into your activity, you'll see that you can augment it a few times and hopefully pop that thing up to a value of 35. This process of breadth first actually ended up taking 6 total augmentations, which is not optimal. And we'll actually see that even in the depth first version of it. But it did do the job. It got to my ultimate flow value of 35, which is great. And then example 3 is then going to be our matching one that we looked at just at the kind of cute little one-off in the last section. So we had 5, workers or people or tasks or whatever you wanted to view those with, and then 5 other workers, tasks, people, or whatever you wanted to. We had some weirdo connections between them. And then if we introduce this source and sink, we can actually turn it into a flow problem, which means that we can just nicely apply this forward Fulkerson. It's going to take 3 augmentations, basically going from no match to 1 to 2 to 3, and then finding no additional matchings to be had. It's then going to return back to the user the optimal flow, which is 3. It's kind of clunky at the very end because it's this massive flow. Or a massive flow network, and that there's 12 rows and 12 columns. Most of the stuff that we care about is only going to be living around here, so like kind of top right corner. So all I'm going to do here is I'm going to look in that top right corner and try to find out where the 1, 1 terms are. I'm not going to look in the top row because that's going to be from matchmaker outward, and that doesn't tell me anything. And I'm not going to look at that very far right side of things because those are all going to be matched people back into sync. So they'll tell me who is being matched, but it won't tell me who they're matched to. So those ones are the things that are then going to exist in the middle. So you can see that little 1, 1, you can see that little 1, 1, and you can see that little 1, 1, which are then going to connect to 1 being paired with 6, 2 being paired with 8, and 3 being paired with 7. So if you remember, 1 and 2 were both connected to 6. So the moment that 6 was used up by 1, then 2 needed to go look elsewhere, which they found in 8. And then 3 could match up with 7, and then we couldn't do any farther, which you can actually see is exactly what happened in our flow process. So if I switch things up one little tab over, I have a nice copy and paste of absolutely everything that we had on the previous bit, except for the way that the forward Fulkerson algorithm is going to run is now going to use a depth first process. So as before, we had this breadth first process, which used queues. Here I copy and pasted our depth first process, which then uses stacks. So here I'm going to push things onto the stack, and I'm always going to grab the last thing that was entered. So instead of having a pop with a 0, it's now just going to be a pop with no 0, which means it's always going to grab the last thing that was actually added. What's fun about this is that you can run this thing and you're going to see that it's going to gravitate towards the larger vertex labels, because that's what's going to be last added to this. And you'll see slight variations. So our Canadian example is still going to have a flow of 23, and it's still going to be done after 3 augmentations. But the way that it did it is a little bit different. It did the bottom route first, then it did the zigzaggy through the middle route, and then it did the top route. In your activity example, we actually ended up with only 5 augmentations rather than 6, but we get obviously the same flow value of 35. So we have those 5 augmentations. And in our matchmaking, we still ended up with a match of 3, but you can see here that we gravitated towards slightly larger numbers. So rather than pairing 1 with anybody, it's now got 2 and 6, 3 and 9, and 5 and 8. So everything is gravitating slightly towards larger numbers, just because that was the stuff that was last added in our big old tree design. So it's kind of fun to just play around with things. All we need to do is change how you designed the tree. And if you change how you design the tree, everything else is then carbon copy the same. So it's one little piece in the middle that can be changed up. So if you want to try to optimally design your tree by using biggest weights as possible, you might get slight variations. If you want to do things purely random, if you want to do things any way you see fit, basically create your favorite spanning tree that's going to go from source down to sink. If you can find that, then you can build a path, and then you can do augmentation. So rinse, repeat, rinse, repeat, rinse, repeat, and play around with it for a little bit. So it's pretty cool. I'll give you this code. Feel free to change it, modify it any way you see fit. As I alluded to before, I went with just kind of the most readability version of it, not with the most like Python-y implementation of it, and that you could easily transition it into some other language, and that I just kept very basic for loops and if structures and things like that. So you don't have to, go recreate everything. You can just be like, well, that structure here is literally copy and paste it into something else. As long as I can index things and do things maybe a bit dynamically, life is going to be great. So that's there to be played with. You'll have a few more examples in some homeworks and activities. So you'll have a chance to modify things, play around with them, do anything you want to with them. So have fun, enjoy, chat later.